One-dimensional motion is the simplest form of motion in physics, and there are many examples. 100-meter dash races, pinball machines where the ejector sends the ball going in one direction, unlucky gutter balls in bowling, land speed record breaking, and drag races. The study of motion is called kinematics in physics. It's a good portion of classical physics, and it's mostly attributed to one man named Isaac Newton, who's quite possibly one of the greatest brains in recorded human history. And what Newton noticed was that his variables, distance, acceleration, and velocity, did not have a conventional algebraic relationship. So he had to develop calculus, which was primitive at that time, to drive these equations. Now this is what he noticed. He noticed that acceleration, A, was the first derivative of velocity. Also he noticed that velocity itself was the first derivative of distance. If you have a calculus background, you know that x would be the integration of v dt, and that v itself was the integration of acceleration dt. Assuming that the acceleration is constant, this would be at, a times t, that's acceleration times time, plus initial velocity, that's v. That's a very important equation. Let's call it equation number 1. And if you go back to this one and plug in the value of velocity, x would equal the integration of velocity, which is acceleration times time plus initial velocity, dt. And this is nothing but a linear equation. This would equal, x would equal 1/2 acceleration times square plus initial velocity times time plus the constant, which is the initial distance. Now, if you don't have a calculus background, we'll develop these relations in a different format. This is equation number 2. These here are the equations for one-dimensional motion, and each one of those has an advantage. For example, this equation here, which is the same as this one here, has an advantage that you don't need to know distance. You don't need to know how far an object went to use it. So if you need the final velocity or the initial velocity, any one of these unknowns, you need the other 3, but you don't need distance. And this one here, time is not a factor. Notice you have final velocity squared equals initial velocity squared plus 2 times acceleration times distance. You don't need to know time. And if you look at this equation here, you don't need to know the acceleration. So each one of these has an advantage. And the way they were driven using algebra, I could show you how it's done. Let's try it. Now we know that velocity, which is speed, equals distance, the change in distance, delta x over t. Velocity equals distance over time. And we know this from speed in cars, miles per hour, etc. The change in x is x minus initial x over time. Cross multiply, and you'd have x minus initial distance equals velocity times time, and x would equal velocity times time plus initial distance. V here is an average velocity. Which is initial velocity plus final velocity divided by 2. That's average velocity. And t here, if you remember the first equation, which is final velocity equals initial velocity plus acceleration times time, t would equal final velocity minus the initial velocity divided by acceleration. So if you were to take this part here and plug it for v, and this plug it for t, x would equal v, which is this term here, initial velocity plus final velocity, over 2 multiplied by t, which is final velocity minus initial velocity divided by acceleration, plus the initial term here, which is initial distance. Now once you work this out, you will have final velocity squared minus initial velocity squared divided by 2a plus x 0. Subtract the initial distance from both terms. You'll have x minus x sub 0 will be equal final velocity squared minus initial velocity squared divided by 2 times acceleration. We know that this term is the change in distance, delta x equals final velocity squared minus initial velocity squared divided by 2 times acceleration. And when you work this out, you'll have final velocity squared would equal initial velocity squared plus 2 times acceleration times change in distance. This is a good equation because it doesn't involve time. And this is this equation. And if you look back here, a lot of these equations were linear. The x-axis here is time, and this is distance. Let's call it x. And you have a relationship of such. If we were to observe an object in motion, we'll notice that, let's say we started to observe at this time here. Let's change the color. If we start to observe here, and we stop observing here, this here would be the change in time. And if we look here, and here, this reading on the x-axis would be the initial distance. This would be the final distance, which means that speed equals the change in distance over the change in time. In other words, this is rise. Notice this triangle. This is the rise, and this is the run. It's rise over run. Also, the change here means the first derivative, which means v equals dx over dt when you take the limit. I think all these principles are a lot easier to conceive in numerical form, which means we're going to have to do an example. And we'll do an example next.